Hello everyone, I'm Martin Berg. I'm a faculty member in the Mechanical Engineering Department at the University of Washington. And in this video I will introduce you to MATLAB's append and connect commands. And I'll do that via an example. So first of all, append and connect are a couple of MATLAB functions that are simple and yet very powerful for developing MATLAB state models of complex linear and time-invariant dynamic systems. In this video, I hope to illustrate that by application of append and connect to create a MATLAB state model of the closed-loop system represented by this block diagram. Now, there's nothing special about the dynamics of this system, but it involves a plant in the feed-forward path. The plant has two inputs, a control signal U and a disturbance input signal D. The plant has a single output theta. The plant includes, say, an actuator model, 1 over tau s plus 1. The actuator generates an actuator signal V. Also in the feed-forward path, we have a first-order controller that has its own 0-1 pole. The controller operates on an error signal E to produce the control signal U. The error signal E is the difference between a reference input signal theta ref and a perfect measurement of the output theta. Now for this MATLAB state model I wish to generate, I have some specific ideas about what the input and output vectors should be. Namely, I want the input vector to have two elements, the first one being theta ref, the second one being the disturbance input D. The output signal is 3 elements. The first element I want to be the output theta of the plant. The second one is to be the control signal U, and finally the third one is to be the actuator signal V. The process for creating this state model using MATLAB's append and connect commands involves fundamentally 2 steps. The append step followed by the connect step. For the append step, we'll need to define some subsystems. I've made a particular choice here of 2 subsystems. The controller subsystem shown here, the plant subsystem shown there. Many other choices one could make for the subsystems. This just happens to be the choice I made for this example. In this slide, I want to show you the specific code that I wrote in MATLAB to implement the controller subsystem. That code is shown here, and before I go any further, I want to point out that the code that I'm showing you here and on all the other slides in this video, it's available and it's part of a MATLAB M file, appconddemo.m, that is available now on the course webpage, so you're welcome to download it and run it and whatever, modify it or do whatever you want with it. In any case, appconddemo.m includes these lines of code. It uses the MATLAB TF command to define the controller subsystem. The TF command, the way it works is the first argument needs to be a vector of the coefficients of the numerator polynomial in S. The second argument is a vector of the coefficients of the denominator polynomial in S. So in effect, the numerator polynomial is k times S plus z, and the denominator polynomial is S plus p. In order for this to work, we of course will have had to define values for k, z, and p. Those values are defined in these 3 lines above, and in connection with that definition, I'm using another MATLAB M file, input inptdf.m. This is a little M file that I wrote. It's available now on the course webpage. Input df.m, it accepts as a first argument a prompt that it then prints out on the command window for the user. For example, this prompt tells the user to enter a value for k in units of Newton meters per radian. It specifies here that if the user hits simply the return key, the M file will accept for k the default value of 10. Similarly, this guy establishes a value for z, printing at the command line the prompt enter z in units of 1 over seconds, the default value being 1/100th, etc. for p. So here I just wanted to show you specifically this inptdf.m file. It's very simple, 7 or 8 in total lines of executable code. The main point being, if you want to run appconDemo.m on your machine, you'll need to have a copy of inputdf.m in your MATLAB path. But that's all it is. Okay, moving on, the plant subsystem. The plant subsystem is a little more complicated. 2 inputs, third order dynamics, a single output. For that, I first converted from Laplace domain to the time domain. Hopefully you remember that, let's see, this transfer function 1 over tau s plus 1, the input is u, the output is v. In the Laplace domain, the dynamics can be written this way. If you convert to the time domain, the dynamics can be written as v dot is equal to 1 over tau times u minus v. Similarly, for the rest of the plant involving the input, let's see, the disturbance input d and the actuator signal v, those dynamics are described in the Laplace domain by theta dot of s is equal to 1 over js plus b times v of s plus d of s. Converting from here, the Laplace domain, back to the time domain, we get this guy, j theta double dot plus b theta dot is equal to v plus d. Or equivalently, solving for theta double dot on the left-hand side, we get this differential equation, second order differential equation. So those are the differential equations that make up the subsystem of my plant subsystem. This is a state model that I generated not in MATLAB, but on the side and in my own notes. This is a third order state model description of these dynamics. The state vector is, let's see, theta dot over theta over v, and these fall right out of these differential equations you see up here. So that's my own write-up of the state model to be implemented in MATLAB code. Here's the MATLAB code that I generated to actually develop those state model matrices. And you can see here that first I use the input df.m function that I wrote once again to determine a value for tau, a value for j, and a value for b. Once those values are obtained, I go on to define the state model matrix A, and you can see this is simply the MATLAB, a way to write in MATLAB that the A matrix I wish to generate is the A matrix here in the square brackets on the left. And similarly, the B matrix is a, let's see, 3 by 2 matrix with, I mean, it's pretty obvious, I think, what the elements are. And similarly, C is the 2 by 3 matrix, and D is a 2 by 2 matrix of all zeros. So here in MATLAB, we define the A, B, C, and D matrices for the state model. And finally here, I call MATLAB'S SS command. And if you are not familiar with MATLAB'S SS or state space command, MATLAB SS command here will define a state model dynamic system object that is going to be named plant, and the arguments to the SS command are the state model matrices in order A, B, C, and D. So next, in this slide, we're back to thinking about the big picture for the moment. Recall that we're out to create a state model of this closed-loop system using MATLAB's append and connect commands. And in this block diagram, I specifically labeled our 2 subsystems, the controller subsystem and the plant subsystem. So in the first step, the append command, we're simply going to append the controller and the plant subsystems together to create the appended system. The MATLAB code for that is here. It's very simple, really one executable line of code involving a call to MATLAB's append function. The arguments to the append function are the subsystems to be appended, And the return argument is the name of the dynamic system object that will be the appended system. In block diagram form, what the append command does is it creates a parallel combination of the subsystems. And it's crucial that you realize that the order is important. When I called the append command here, the order of the subsystems was number 1, the plant, followed by number 2, the controller. And so in my block diagram of my appended system, the corresponding order is the plant is number 1, the controller is number 2, and note that that implies that, hey, the appended system will have 3 inputs. In order, they will be U followed by D followed by E, and 3 outputs. In order, they will be theta followed by V followed by U. So that's all there is to it in terms of creating this appended system. In the next step, we want to implement connections that create the closed loop system from the appended system. We'll move on in this slide to do exactly that. And I want to start off with a conceptual review of what it is we're about to do. We're interested in creating a state model of this closed loop system, and we want that state model to have specific input and output vectors. Namely, for the input vector, we want the input vector to have 2 elements, the first being theta ref and the second being D. We want the output vector to have 3 elements. In order, they are theta and U and V. Above here, I show a white box representing my closed loop system with the input and output vector elements. And I just want to reiterate that the order of these guys is important. We want the number 1 input to be theta ref, the number 2 input to be D, and for the outputs, we want the output elements in order to be theta over U over V. So that's conceptually what we're about to do. Now, to get down to the brass tacks, if you will, we have an appended system, and I claim it's quite straightforward to determine the connections to be made among the inputs and outputs of the appended system and the inputs and outputs of our closed loop system to create the complete closed loop system dynamics. Indeed, I hope you will come to realize, perhaps with a little bit of thought, that the connections to be made are shown in living color in this diagram. Looking at it a little bit more closely, you can see that we've connected the theta output of the plant to the theta output of the closed loop system. We've connected the V output of the plant to the V output of the closed loop system. We've connected the U output of the controller to the U output of the closed loop system. And on the input side, we've got 2 inputs for the closed loop system, theta ref over D. We've connected the theta ref input of the closed loop system to the E input to the controller. And we've connected the D input to the closed loop system to the D input to the plant. And perhaps most importantly, we've got some feedback connections shown here in red. Specifically, we've connected to the U input to the plant, the U output of the controller with a plus sign in the feedback path. And we've connected to the E input to the controller, the theta output of the plant with a minus sign in the feedback path. So those are the connections to be made to create our closed loop system from our appended system. The last thing to be determined is how we communicate that to MATLAB so the connect command can do its job. That communication, it turns out, is via the definition of 2 vectors and 1 matrix. One of the vectors defines the output connections shown in blue on this figure. The other vector defines the input connections shown in green on this figure. And the matrix defines the feedback connections shown in red on this figure. Next, I want to go through carefully the definition of these 2 vectors and 1 matrix that define to the connect command the connections shown in color on this figure. Starting with the output connection shown in blue, to communicate that information to the connect command, I define a single vector. I chose to call it OUT-PTS. You can call it whatever you want. Most importantly, this vector has 3 elements. to correspond to the fact that our connected system, which will be the closed loop system, is to have 3 elements. Each element is strictly a positive integer. The number 1 element is a 1 to communicate to the connect command that the first output of the connected system is to be the number 1 output of the appended system, indicated by this arrow here. The second element is a 3 to indicate to the connect command that the second output of the connected system is to be the third output of the appended system, as indicated by this up arrow here. And finally, the last element, the third element of the outputs vector, is a 2 to indicate to the connect command that the third output of the connected system is to be the second output of the appended system, as indicated by this blue arrow here. Now, I've added a little bit of text here to kind of make this a little bit more explicit. This output vector needs to be a vector of strictly positive integers, and if the ith element of it is j, the connected system's ith output will be the appended system's jth output, which I believe is what I just said 30 seconds ago, so we won't belabor that. So next we'll move on to deal with the connections at the input side of our system shown in green on this figure. And for that we'll define a vector. I named the vector INPTS. You can name it whatever you like. Most importantly, the vector has 2 elements to correspond to the fact that our connected system, which will be our closed loop system, has a vector input that has 2 elements. Each element in this vector must be a strictly positive integer. In this case, the number 1 element of this vector is a 3 to communicate to the connect command that the first input to the connected system is to be connected to the third input to the appended system. Its second element is a 2 to communicate to the connect command that the second input to the connected system is to be connected to the second input to the appended system. And finally, I've added some words here to make all of this a little bit more explicit. This inputs vector needs to be a vector of strictly positive integers, and if its ith element is j, the connected system's ith input will be the appended system's jth input. So those are the definitions of the vectors that communicate to the connect command, the input and output connections to be made. Next, we move on to deal with communicating to the connect command, the feedback connections to be made, shown in red on this figure. As I mentioned earlier, this entails the definition of a matrix rather than a vector. I chose to name that matrix connects. You can name it whatever you like. Here it is. The first column of this matrix is special. It's special, first of all, in the sense that each element in the first column needs to be a strictly positive integer. These elements indicate the numbers of the appended system inputs to be connected to. Subsequent elements in each row indicate the numbers of the outputs of the appended system to be connected back to the input named at the first column position of that row. The sign in the second and subsequent elements in each row indicate whether the feedback connections are to be made via a positive sign or a negative sign. For example, this first row indicates that the third output of the appended system is to be feedback connected to the first input to the appended system with a plus sign in the feedback path. Going up to our diagram, we're talking about the third output of the appended system to be connected back to the first input to our appended system with a plus sign. Thus, this row needs to be 1 followed by 3. The second row, 3 minus 1, is to communicate to the connect command that we wish to connect the first output of our appended system back to the third input to our appended system with a minus sign in the feedback path. That's this feedback connection here, we're to connect the first output of the appended system to the third input to the appended system with a minus sign. Thus, this row needs to be 3 followed by -1. A paragraph or two to make all this explicit. This connects matrix needs to be a matrix of integers. In each row, the first element is strictly positive and is the appended system's input to be connected to. In the same row, each remaining element is the number of the appended system's output to be feedback connected. If the number is positive, the feedback connection is positive gain. If it is negative, the feedback connection is negative gain. If it is 0, the feedback connection is not made. And I show here that in our case, the connects system is 2 by 2. For more complicated cases, there may be more columns than there are rows in your connects matrix. All that works, and these elements, the elements in the second and subsequent columns, can be 0 as placeholders if no connection is to be made corresponding to that element. So we've completed now the definitions of our two vectors, the inputs vector and the outputs vector, and our one matrix, the connects matrix, that will communicate to the connect command. The connections shown in color on this figure to create our connected or closed loop system from our appended system. All that really remains is to call the connect command. The syntax for that is shown here. We're calling the connect command. Its input arguments are: the first one needs to be the appended system, the second one needs to be the connects matrix, the third one needs to be the inputs vector, and the last one the outputs vector. It creates a dynamic system object that in my append.condemo.m file I've chose to call closed loop. And this slide shows the code you'll specifically see in the append.condemo.m file if you look for it there. Here's the definition of the inputs vector, the outputs vector, and the connects matrix. And here's the call to the connect command. I hope that with a little thought you'll come to realize what a powerful tool the combination of append and connect can be. There's a tendency to think that we should be doing all this sort of thing with a graphical tool like Simulink, but in my experience, being able to do this kind of thing on the command line can be a real time saver. So at this point, some of you may already be thinking that the combination of append and connect is a powerful tool, but it seems like we're having to draw a lot of block diagrams in the process, and can I somehow shorten the number of block diagrams I need to draw to shorten this process overall? And the answer is basically yes, and that gives rise to some shortcuts. And I'm going to show you some of those, but I want to emphasize that when in doubt, you need to go back and draw yourself a diagram in detail to keep track of what's going on, because it's easy to make mistakes, and believe me, I've made many of them. So here's a trick I often use. Here I've drawn a box with my closed loop system with all the connections sort of internally made in this box, and I've put on the outside of this box, I've indicated that I want, for my closed loop system, I want the input to be a vector with these two elements in this order, and I want the output to be a vector with these three elements in that order. So for starters, I'm going to run the append command. I'm going to append the plant and the controller in the order shown here. So up in this block diagram, I will label that the first appended system is the plant, and I put this 1 in the upper left-hand corner. I label its inputs 1, 2 in a certain color. I label its outputs 1 and 2 in another color. The second system in my appended system is the controller, and so I'll label that with a 2 in its upper left-hand corner, and simultaneously label its input. Well, it's going to be the third input to the appended system, because this guy already gave rise to 2 inputs, and the third output of the appended system is going to be this guy, because this is the second system in the appended system. So I've defined now my appended system, and from that, with a little careful thought, it's fairly easy to come up with the definitions for the inputs, the outputs, and the connects matrix. Just with a little pondering of this diagram, it's pretty easy to see. For example, we can see that for the connects matrix, we need to connect to the third input of the appended system the first output with a minus sign, and that gives rise to this row here. In any case, this is one example of a simplification to the process that you're welcome to take, but again, be careful, and if you don't seem to be able to get a closed loop system that behaves as you think it should, go back and double check and triple check to see where you might have made an error in defining these two vectors and this one matrix, because it's very easy to make mistakes there. So finally, I included this slide simply to drive home the point that there's nothing magical about the two subsystems that I've shown you so far in this example. I could have just as well have picked, say, 4 subsystems, say these 4. Here's the actuator. I could have made the actuator as subsystem number 1, this portion of the plant as subsystem number 2, this pure integrator part of the plant as subsystem number 3, and the controller as subsystem number 4. I then would have called the append command with these 4 subsystems in the order shown as arguments, and then also, of course, the definitions of the inputs vector, the outputs vector, and the connects matrix would have all needed to have been different to end up with the correct model of our closed loop system. This ends my discussion of MATLAB's append and connect commands. They are powerful tools, and I wish you well with them. If nothing else, this way, when I post M files on the course website and you pour through them, you'll have a shot at least at understanding what in the world I was doing when you see all these append and connect commands in the code.